Hi, we are Manan Gandhi and Rachel Schlossman. Today we will be presenting our tutorial paper on GATE, a GPU accelerated trajectory evaluation tool. Let's get started. GATE is a tool designed for rapid Monte Carlo simulations for complex dynamical systems. The primary benefit of GATE is a fast plug-and-play approach to underlying dynamics, controllers, and perturbations. This tool allows for fast evaluation of controller robustness against a wide variety of perturbations and disturbances through parallel simulations, i.e. rollouts. This allows the user to develop complex simulations with parameters that can vary in time as well as on a per rollout basis. Our case study for a quadrotor system shows that GATE outperforms other parallel simulation technologies using CUDA, C, and C++. CUDA, the Compute Unified Device Architecture, is a programming interface based on C, which allows users to take advantage of massive parallelism offered by GPUs for general-purpose programming. The key points to be aware of is how memory is handled between the CPU host and the GPU device, and how many individual processes are run via the CUDA kernel. GATE is designed to allow the user to easily implement classes whose memory is managed automatically on construction and destruction. Transferring data to and from the GPU is handled by a simple API, and the user is empowered to increase the complexity of their dynamics, controllers, and perturbations as needed. GATE simplifies the process of handling memory and has a custom kernel written to execute multiple trajectories at once, along with complex control systems. The core of GATE lies in the template classes for dynamics, perturbations, and control. The user will instantiate each of these templates for their desired problem, then be able to run the rollout kernel. Inside the rollouts, the namespace integrators contains the different implementations for integrating ODEs. This namespace is also extensible for users that would like to implement other integration schemes. Dynamics implements a state derivative computation given a control input and set of perturbations. This can be modified to represent multi-phase hybrid systems, such as systems with contact dynamics. Controllers implements various control strategies designed by the end user. Support for per rollout parameters, such as the integral error accumulation term in a PID controller, allows for adaptation of the controller based on the simulation. The perturbation class implements variation in the initial condition and in the control channel. Support for variation in parameters in both time horizon and number of rollouts allows us to test the robustness in a wide variety of conditions. The base class, perturbations, is provided to the user, which implements perturbations in the initial condition and control. The user then specializes the base class into the class perturbations, where the individual system parameters can be varied. Next, Rachel will go through some examples and implementation details of the GATE library.
To demonstrate the architecture of the GATE tool, we will be going through a couple of examples that are available in our public GitHub repository.
We will now show how we can implement a Monte Carlo evaluation of a Dubin's vehicle with proportional feedback control. So as we know, we need to make system-specific dynamics, perturbations, and control classes. So first we'll look at the nonlinear dynamic equations. Our state variables are the point masses x and y positions in the masses heading, theta. V is the constant speed of the point mass, and omega command is the angular velocity command. For perturbations, there are two sources of uncertainties in the system, initial condition disturbances, and control input disturbances. W is normally distributed white Gaussian noise that introduces uncertainty through the input control signal. The initial conditions are also normally distributed with a user-defined mean and standard deviation. Then the control law in the right column is designed to drive the vehicle to a desired XY position. We use a proportional controller that feeds back heading error. Now we can look at how each of the classes are implemented for the Dubin's vehicle. You can see that the Dubin's param struct is where we can initialize system-specific parameters. In this case, we have a default constant speed as well as control limits if we want to implement them. In the Dubin's dynamics constructor, we instantiate an instance of the dynamics class. If we go to the definition of the dynamics class, we can see that in the dynamics streamed manage file that the dynamics class is templated to accept arbitrary system dynamics, arbitrary params, as well as an arbitrary state dimension and control dimension. The dynamics class is what actually moves the Dubin's dynamics and params to the GPU. Going back to the Dubin's dynamics script, compute state derivative is where we implement the dynamics equations of the Dubin's vehicle.
Every system simulation has a system-specific perturbations class. So in the Dubin's perturbation class, if we go to its constructor, we can see that we instantiate an instance of the perturbations class. The perturbations class applies to all systems and allows for initial conditions and control input perturbations to be generated from a normal distribution and moved to the GPU. If there were other uncertainties that we wanted to introduce into the Dubin simulation, we would do that in the Dubin's perturbation class, specifically under the init perturbations, allocate CUDA mem, and deallocate CUDA mem functions.
For the control design, we nominally have a proportional integral controller as shown by the non-zero P and I gains in the Dubin PID param struct. I'll later show you how we modify these parameters. Scrolling down a bit, the guidance class in guidance-stream-manage.cu and .cuh passes all things guidance related to the GPU. The get control function shows our implementation of our feedback control law, and then at the bottom of this function, this highlighted block shows how we incorporated the input control perturbations.
So now we'll show how we tie all the pieces together to run a parallel simulation of the Dubin's dynamics. So for every simulation that you run, you'll want to specify a time step, the number of time steps for each parallel simulation, and the number of parallel simulations you want to run. Here is where we create our Dubin's dynamics and Dubin's control objects. Here is where you'll make any modifications you want to the guidance and dynamics parameters. In this case, we modify the time step, proportional, and integral gains of the control params as well as the desired position that we want to reach. And then we set guidance params, set dynamics params, and set params for the control and dynamics classes. Here's where we set up the perturbations for our simulation. So specifically, we specify the mean and the standard deviation of each of our 3 states, and then we specify the standard deviation of our control input disturbance. Here's where we initialize the Dubin's perturbation object, and then here is where we send the perturbations to the GPU. The RTE object is what ties together the dynamics, perturbations, and guidance classes, and then this object calls the compute trajectory function. So if we go to the compute trajectory function, in particular, this function is what calls for the parallel simulations to be run on the kernel. Specifically, it calls rollout kernel RK4. So if we then go to that definition, basically what this is going to be doing is integrating our dynamics forward in time for each of our parallel simulations. So we can see that we are checking that the thread ID is less than the number of rollouts, and if it is, we will run a parallel simulation. So this first step for each of the parallel simulations will be to configure the initial conditions, and we do that by grabbing the information that we need from our initial condition perturbation variable that is located on the GPU. After we configure the initial conditions, we'll integrate the dynamics forwards. So we do that using a for loop going from the first time step to the number of time steps. So every time we step through this for loop, the first step will be to call the guidance class's getControl function to get the control signal we want to send to our dynamics. Then to send that computed control signal to our dynamics, we have to call an integration scheme to propagate our dynamics forward in time. In this case, we use the RK4 algorithm, but one could write their own integration scheme if they want. When we look at this RK4 algorithm, we can see that we call a arbitrary dynamics class compute state derivative function. Notice that we pass it the perturbations in case we want to perturb anything in the perturbations class. So basically, after all the parallel simulations are run in gate.cu, we can save our trajectories. So just to show you how we set up the executable, you do that in your cmakelist.txt. So we'll run that, and basically we can see that we run our parallel simulations in 17 milliseconds, and then the rest of the time we'll be exporting our trajectory to a CSV, and then we also include a plotter in the repository to be able to plot the results. Here are the results with 500 rollouts and the state and control input perturbations we have discussed. Most of the trajectories are able to hit the target. One particular trajectory in pink curves away from the desired position early, which corresponds to a missed distance greater than 1.5 meters. To show the performance boost achieved by using GATE, we consider a quadcopter case study that's in our paper. We implement an LQR controller, and an example of the trajectories with inertia uncertainty is shown. To compare different frameworks, we implemented analogous versions of the quadcopter simulation using GATE, NumPy, SIMD vector operations, NumPy, SIMD vector operations pooled across 8 CPUs, CuPy, PyTorch batched operations on the CPU, and PyTorch batched operations on the GPU. We simulated 15 seconds of flight. The left diagram shows that the GATE implementation performed best across the full range tested, with batched pool NumPy as the runner-up. So as we've seen, GATE provides a tool with a modular structure that allows you to plug and play with different dynamics and controllers and perturbations, and allows for fast simulations. In the future, we would like to incorporate variable time step integration schemes, as well as the use of multiple GPUs to increase the number of parallel simulations that you can do. Thank you for your time, and feel free to reach out via email if you have any additional questions.